Today's problem is remove BST keys outside given range. Excuse me. The difficulty is medium. Given the root of a binary search tree and two integers, L and R, remove all the nodes whose values lie outside the range L to R, inclusive. Note the modified tree should also be a binary search tree. I wish they would call these low and high instead of L and R, but so I think it's pretty clear what we want to do here. We get a binary tree and a range of numbers, and we remove any node with a value that's outside that range. You could do that with, an in-order traversal. One way is you could just, when you find a node that's not in the range, just delete it, rebalance the tree. You could traverse the tree, keep all the nodes in the range in sorted order, and rebuild the tree. I don't think either one of those is optimal. They're probably still O of n, but I think the multiplier is going to be much higher. Constraints. Number of nodes is between 1 and 10 to the fourth, 10,000. The data is between 1 and 10,000. L and R are between 1 and 10,000. R is greater than or equal to L. So that's good to know. Time complexity, O of n. Auxiliary space, O of n. I think for the recursive stack. Topic tags, binary search tree. Okay, yeah, so in this case, we will get a binary search tree of which some of the nodes will be within the given range. Is that true? Well, let's say 0 or more will be within the given range. In this case, negative 10 to 13. So the nodes that are within the range are the 6, the negative 8, the 13, and the 7. We'll come back to that one. That one's a little bit easier to look at. This one, it's a bigger tree, but it's a smaller range. So the only nodes that are in the range are the 4, the 2, and the 3. Okay. We do a post-order traversal here, and every node we compare the value with the given range. Now, if the node's value is less than L, then that means that all the nodes in the left subtree are also smaller than L because of the property of a binary search tree. So we'll just throw out the whole left subtree. So that's good. Similarly, if the node's value is greater than R, then all the nodes in the right subtree are going to exceed R, so we can discard the right subtree and return the trimmed left subtree. If the node's value is within the range, then we keep it and attach the recursively trimmed left and right subtree. Yeah, so let's look at this tree here. So we're looking for node values between negative 10 and 13. So when we hit this 14, that's too high. So not only do we want to get rid of the 14, but we want to get rid of the entire right subtree of the 14. Now you may say, well, but it's only one node. In this example, yeah, it's only one node, but a tree can have on the order of 10,000 nodes. So potentially there are thousands of nodes over here that we don't have to look at because we're able to use this property of a binary search tree effectively. So something like this, we would look at it and say, well, where are we doing that? Okay, so this is the post order traversal. You do the subtrees first. Check the data. Is it in range? If so, then you can use the left and right subtrees, which we have already processed with the post order traversal, the depth first search. Or we check to see, is the root data less than L? In this case, no. The only other option is that it's greater than R, and so we just return the left subtree, and we don't consider the right subtree at all. That's what that's doing. All right, so that should be enough to get us a solution. Let's try it. Okay. Okay, good. Yeah, actually, I submitted this once before with an in-order traversal, but I really tried to use the property of binary search trees, lower values to the left, higher values to the right, to prune the search space, but it's still timed out. So yeah, this problem is actually pretty strict, I think, on the timeout. But yeah, anyway, so that's it. Please go ahead and like the video. You can subscribe to the channel as well, and we'll see you next time.